Okay, go. Janice! What? Guess what we're gonna do today? What? Physics! Yay! Did you know you're doing some right now?
Oh, I am?
Yeah! You know, Newton's third law states that for every action, there's an equal and opposite reaction. And so, when your body pushes force down on the bed pushes force on you.
Really? So they balance out?
Yeah!
Whoa! Weird!
I know! We should get some breakfast.
Okay. What are you doing?
My reflection. It's in the spoon.
You know why you can see your reflection in the spoon, Rachel?
Tell me, Janice.
Well, you see, the spoon is made of a smooth material. And
Yes.
so, the light that goes down and shines on your face and onto the spoon reflects off of it so that you can see your image inside of it.
No way! What should we do next? Let's play with eggs. Hey Janice, I bet you can't break this egg just by squeezing it.
Oh yeah?
Yeah.
I accept your challenge.
Good.
I can't break it.
Yeah, I know. The thing is, no one can.
Why is that?
You see, the egg has one of the strongest shapes possible. Because it's parabolic, the force applied, being your hand, will be spread out evenly throughout the entire egg. So no matter how hard you squeeze, it'll just stay like that. And that's why when most people need to break an egg, they just go.
Because then the force is applied to only a small section of the egg, which is very weak only by itself.
And my mom will not like that. Janice! What? I challenge you to a bubble war! You see? No!
Rachel!
What?
I noticed something!
What?
Have you noticed that there are colors? Oh. In the bubbles?
You're right!
Why is that?
Well, when light travels in through the bubbles, there are actually two layers. There's the outer layer, and then about a millionth of an inch later is an inner layer. Both of these layers reflect the light. Now, because these two waves kind of interfere with each other, they'll cause a lot of different colors, and you'll see those as they just kind of swirl around. However, if the two layers of the bubble get too close to each other, then the bubble will then You know, Janice?
Yes?
We should probably get going to school.
Yeah.
Ah, Janice! How did you do that?
Well, you see, Rachel, whenever I wiggle around on my chair like this, the electrons from the chair transfer to me and build up a charge in me that's greater than the one that I normally have. And so, whenever I reach over to you, the electrons jump from the tip of my finger onto you to balance out.
Oh, well, stop doing that. Ah, that one actually worked. Okay. So then I'm like, your butt is so big. And she was like, nuh-uh.
Hey,
And
Rachel,
what?
you see that bottle right there?
I do see it.
You know what is being demonstrated there by that bottle right now?
Nothing!
No,
Oh.
actually, it's Newton's first law.
Really?
Yeah. Newton's first law states that an object at rest will stay at rest unless acted upon by an outside force.
Uh-huh.
Well, I don't see any outside forces around. Ah, Janice. Now you do. And I just demonstrated the other half of Newton's first law, which is an object in motion will stay in motion unless acted upon by an outside force.
Our outside forces must be gravity and friction.
Yeah!
Nice. You see this? What? With the water I'm making a rainbow.
A rainbow!
You see this? And you see, when the water is sprayed and coming towards me, when the water is sprayed, the light actually goes through the water droplets almost like it did with the bubbles. Except now there's only one thing, so all the light waves are converging, meaning they're all going the same way. And that is how you see the rainbow. And actually, as most people think, rainbows are circles. As you can see when I move the hose, it goes in a circle rather than just an arc.
It does.
Cool.
Yeah. So, Rachel,
Yeah.
what's for dinner?
Potatoes!
Oh!
Yeah.
Hey, you want to see a trick?
I do.
Potato.
Yeah.
Straw.
I see. Whoa! Let me try.
Not that way, Rachel.
What?
There's a physics explanation behind this.
Okay.
Okay, so the reason why this works is that the straw has a very small surface area. See, the surface area is only the ring right here where the straw actually is.
I see.
And the potato has a really large mass compared to the surface area of the straw.
Mhm.
So, when we apply an instantaneous force to the surface of the potato with the small surface area of the straw, it goes straight through, like butter.
I like butter on my potatoes.
Me too.
You know, Janice, I never really realized how much physics we actually do in our lives every day.
I know. It's really interesting to know that all the very, very cool things that we learned in Miss Hood's physics class are actually very applicable to everyday life.
I know. I wonder what we're going to do tomorrow.
I guess we'll just have to wait and see. Go. I should?
Yeah.
Say what?
Physics is awesome.
Physics is awesome! Rachel,
Hmm?
look at your spoon. There's a mirror in your spoon.
So there is, but why am I upside down?
Well, you see, the smooth surface of the spoon makes it reflective. And since the spoon is curved in like this, it is a concave mirror.
Let me redo that one.
Sorry, I'm really bad at it.
The egg has actually one of the strongest shapes possible. It has kind of a parabola, and so when force is applied to it, it's I can't remember what I'm supposed to. Throw it behind you on 3. Or are you filming?
Mm-hmm.
Oh, okay. Well then.
You want me to restart?
When the light goes through the bubbles, it kind of refracts, which is like reflecting, except it goes in multiple times. I don't know what refraction is. I hate.
So, Rachel, what's for dinner?
Potatoes! Whoa! I want to try.
Not that way, Rachel. There's a physics thing behind this.
Explanation. 16. Janice! Oh God. I almost fell. Janice, oh God. Rachel! What?
You know what you just demonstrated?